Good evening, everyone. In this video, I want to go ahead and derive for you some of the kinematic equations that the book gives you. And so what I have here shown in these three graphs is the motion of an object that has constant acceleration. In all these different graphs, I have a position time graph, a velocity time graph, and a position time versus time squared graph. You have to remember all of these graphs are showing the same motion but just in different ways. And so what we're doing is we're trying to come up with equations that we can use to model constant acceleration so that we can find unknown variables and do some calculations. So the first thing I want you to notice is that in the center graph is that velocity versus time graph. We looked at that and it was linear, and you'll notice that the slope of that graph was the acceleration. And in this case, there was no vertical intercept. But if we wanted to put one in there, what does the vertical intercept mean? Well, that's just the starting velocity. Now, in this case, it was 0, so that term dropped away. But if you look back in the book, you'll see equation 2.11. There's our equation to find the final velocity of an object if we know the acceleration and the initial velocity and then the time it's been moving. That equation is just our definition of acceleration. If I rearrange it, I could get to that equation as well. So this other equation is talking about position. And when we plotted this graph, you'll notice that the slope ended up being 1/2 of that acceleration term. From the first equation, it was exactly half. So there's my little 1/2 of the acceleration. It had the same unit, which is half as big, and then it was delta t squared. Now, in this equation also, because there's a vertical intercept here, in this case it was 0, we didn't have another term. But you may also see that if there was an initial position, if it started out not from a 0 position, we would actually see that graph someplace else. So we're going to come back to that equation in a moment, relating those two things. But I want to talk about, to come up with some more models for constant acceleration, we need to look at situations that are a little more complex. So my question is, what if I had a non-zero starting velocity? So it's actually already moving when I start taking time, or it's actually already in a position that's not 0. What would we do? And so, for example, if I'm looking at this graph here, maybe I'm talking about from 2 seconds onward is where I started taking data, and I don't really know what happened before that, but I have, after 2 seconds I know the velocity, but before that I don't know. Am I out of luck? So let's go ahead and take a look at that situation. So what I've done is I've expanded this graph. I'm going to redo this for you a little bit here. And I'm going to take that little chunk and I'm going to put it over here. And it started moving at some point, but we don't really know what happened before this. So what I want to do is I want to look at, here's my velocity versus time graph. Velocity versus time. And we're going to take a look at some key pieces about this graph. Okay? So we're going to call this time when I start taking measurements, Ti. And the final time when I stop taking measurements, Tf. So there's on my time. And we're going to call this initial velocity that I started taking measurements, we're going to call that Vi, and it reached some final velocity, and we're going to call that Vf. So there's some important points on this little graph that I've drawn. So when I look at this here, I'm going to go ahead and we're going to try to come up with another equation. And so I'm going to put some names on some of these areas, because if I remember the velocity time graphs, if I take the shaded area under that curve, it tells us something very important, and it tells us the displacement. So I really have two shapes here. I have a square, okay, which is this first little shape here, and then I have a triangle. So I need to add the area of those two together. And if I can find the area of that, I can actually come up with the displacement. And so let's do this first little box here. Looking at our equation 2.11, if I were to rearrange that, rearrange this equation here, subtract Vi from both sides, I could rewrite this as Vf minus Vi is equal to A delta t. All I did was just rearrange that equation. And the reason why I did that is if I wanted to find the height of this triangle, I look up at the top of the triangle and I notice sitting up there that's VF. And I look at the bottom as VI. Now if I take VI minus VF, VI minus VF, that's going to be the height of that triangle. Well, VI minus VF is A delta T. So that means this height of this little triangle is actually just A delta T. I just did a little substitution here. The height of that would be VF minus VI. There's the height. The length of this thing here is to TF, and it's not all the way to TF because there's this little piece here, so I have to actually subtract whatever TI was. So that little length is TF minus TI. Well, TF minus TI is just delta T. So this length here is just going to be delta T, is my length there. So I look at a shape and I notice that the area of this shape is a triangle is going to be 1/2 the base times the height. So my little triangle is 1/2 the base times the height. The base was delta T. The height was A delta T. When I multiply those together, I get A delta T squared. So it's no wonder delta x is equal to 1/2 A delta T squared. When I look back at my position time graph, position versus time squared graph, and I got that equation here, if I were to subtract xi from both sides, I get delta x, final minus initial, is equal to 1/2 A delta T squared. It's no wonder that my displacement was 1/2 A delta T squared. I just confirmed that that was true. And I look back at this shape here. The first time I did this, my area was just a triangle. So it was 1/2 the base times the height, which was the same idea as we just showed. But in this case here, I have to actually add now that other shape, and that would be the square. And so I'm going to go ahead and find the area of that square. Now I look at the height of this little box, and it's going to be VI is the height. That's the height. It's just VI. So that's the height of the box, and then the length of this box is also delta T. So the base times the height, because it's a rectangle, it's going to be VI is the height times the length, delta T. So what I can do is I now have a new equation based on this displacement is the area under the curve. When I go back through, taking what I know about velocity and acceleration, I can actually write displacement in terms of this term here. Okay. Now this is one form of this equation. You'll actually usually see it written like this. Delta x is equal to 1/2 A delta T squared plus VI delta T. Okay, that's going to be one of our big four kinematic equations. I just rewrote it to have the acceleration term first. And I also don't want to forget that I can rearrange this rather easily. Okay, remembering that delta x is just final minus initial. If I subtract xi from both sides, I'm going to get that the final position is equal to 1/2 A delta T squared plus VI delta T. And then I'm going to, it's final minus initial, so I would have to add initial to both sides. Okay, plus xi. This is another form of this equation, and this is actually equation 2.13 in your book. Okay, that's where that equation came from. It's just taking the fact that displacement is just the final minus the initial. So if I add delta, xi to both sides, I can get xf by itself. Okay, so this is going to be a big equation that we're going to use. I'm going to actually erase this box because I like using either of these forms better. I guess it really doesn't matter which order you do it in. So with this being said, there's actually one more equation that we can get. Now, looking back at the equations I've looked at so far, the big two, here's one. Okay, this is one of the big ones that we're going to use. Here's another one. Okay, these two equations here. But if you look at all of these equations, you'll notice that every single one of them has time. all of these equations have time in them. So the problem is if all of these equations have time and I don't know the time, I don't have a way to relate all of these different variables. We talked about final velocity. We've talked about initial velocity. We talked about initial position. We talked about final position. We talked about acceleration. So we have all these variables, including time, and all those equations don't have anything. They all have time in them. So we need an equation that doesn't have time. So what we can do is we can take our original equation, number 1, and rearrange it to solve for delta t. So when I do that, delta t is equal to Vf minus Vi over A. And if I plug that in for delta t here and here, and I reduce this down, I'm not going to go through all the steps, but if you do that, you're going to get a new equation, and when it's rearranged, it's going to be Vf squared is equal to Vi squared plus 2A delta x when you rearrange it. And so that's going to be equation 2.13 in your book. Another very useful equation. This one doesn't have time in it. So if we don't know time, we can still take acceleration delta x and then either of those velocities and solve for something we don't know. Okay, so this has been a little brief recap. The other thing I just wanted you to note was, if I look at this equation here, look at the general form. Y is equal to some constant times x squared plus some other constant times x plus some constant c. This is just our equation for a parabolic variation. But now we actually have some physical meaning to go with all of those terms. And so now if we have an initial position or initial velocity, we can actually calculate some things as well. Okay, this has just been a brief video to explain some of these equations, and I hope it's been helpful.